All right. So last class, we looked at finding the average rate of change, which again was just like grade 9 math, where you're finding the slope of a linear equation. We use rise over run, same idea. Now, this is where things get a little bit different. We're going to find something called the instantaneous rate of change. All right. So we're going to find a little bit different. Now, when we found the average rate of change, so we find an average rate of change between, say, x and some other value. I don't know, x plus a certain amount. And I'm going to call that certain amount h. All right, so we had a number, an x value, and we just added a little bit more, and that's where we found our next point. All right, so if I find the slope or the average rate of change, I would have to find my f2, if you will. And this line, the slope of this line here would be my average rate of change. Now, with an instantaneous rate of change, I just want to find the slope at just kind of a specific spot. So what I would do is I want to move this value closer and find the slope, say, right from these 2 points. Now, I could keep going and keep moving that x value closer and closer and closer to x, and again have 2 points where I'm finding the average rate of change. But what we're looking for here is the instantaneous rate of change. This is a little bit different. So these two here are what we call secant lines, where we're finding the slope of 2 points. Now, for an instantaneous rate of change, we are kind of finding the slope of 2 points, but a little bit different. And I'll get into that. So right here with these two secant lines, we're finding the slope. Say I have another x plus h. Again, h is just a distance after x. All right, so again, we use our formula. Slope is equal to f of, let's see, x plus h, because that's my f2, or y2, I guess you could say. So that's an x plus h, minus our y1, which would be up here, which I would call f of x. Again, just using function notation. And then we have our x2 minus our x1, which would be our x plus h minus x. Again, there's our x2, there's our x1. These would be our y2s, or in other words, our f of x plus h. Now, here's the concept today. If I want the slope at just 1 point, or so close, I want 2 little dots so close together that they look like one. And so this black line that I'm about to draw, I'm only going to draw it through that red dot. And so this black dot, or this black line, that slope is just at that 1 point. And it actually is at 2 points, but the 2 points are so close together that they look like 1 point. And so that would be called what's called a tangent line. Because a tangent line is defined as the slope at just 1 point. And again, it kind of, there is 2 points, but not really, because they're so close together that we can't even tell the difference between the 2 points, the distance. We can't even measure the distance between the 2 points because they're so close together. And so what I've done is I have this x value, and this h is getting smaller and smaller. I keep moving that point, that second point, so close that we can't even tell that there's 2 points there anymore. We can only see 1 point. So this formula, as well, I can actually simplify it as well. So I'm going to do that. So at the top, I have a f of x plus h minus f of x. Now see in the denominator there, I have an x plus h minus an x. So really, I got an x and a minus x. So all that's left on the bottom here is that h. All right, so our formula is changing when we have this concept of a tangent line. Now, as I mentioned, h approaches 0. So that's how I write that, as h approaches 0. So again, I'm moving this second point closer and closer and closer and closer. So close again that there's 2 points, but really you can't tell the difference, so it only looks like there's one. Now, when that happens, it's called a tangent line. So as h approaches 0, again, that's how I write it. We find the slope of a tangent line, not a secant line. And so therefore, our formula that we're going to be using is that the instantaneous, and the reason it's called instantaneous is because you're only finding the slope at just 1 point. Weird concept, right? Because we've always had to find slope in math with 2 points. Really, we're only using 1 point because the two dots are so close together. I can't stress that enough. That it only looks like 1 point. So we call that the instantaneous rate of change. So the instantaneous rate of change at point x here is equal to, here we go, LIM with h approaches 0. I'm going to explain what this notation means. There's our slope for a tangent line up there. We have our f of x plus h minus f of x all over h. So what this is saying is this LIM stands for the limit. We are pushing things to the limit. We are literally taking a second point and pushing it so close to x that we can't even tell that there's 2 points. That's what that means. So the distance between these two x values is essentially 0. It's not 0, but it is. All right? Any questions about that? That's the hardest concept today. Very difficult concept, other than all the equations we're going to do here in a second. All right, so let's try a question here. How does this all shake out? What are we trying to do here? So we're going to go through a couple of examples. All right, so example 1.
Sorry, do you think you could go back quickly just so I could copy it down?
I can't now, no. Sorry. I wish I had done it before I flipped it. I'm recording, so you can always catch it when I'm recording here. And plus the notes on the website. All right, so example 1. Wish I spoke up before I flipped it. A pebble is dropped from an 80-meter high, or a cliff 80 meters high. After t seconds, the height s in meters of a pebble is represented by the equation. So here's our equation here. S of t is equal to 80 minus 5t squared, all over the on the interval of 0 is less than or equal to t is 0 or less than or equal to 4. So I guess this rock is dropping for 4 seconds. It's a nice way of saying that. Now we get to A on the sheet. All right. And A is calculate the average velocity of the pebble between 1 and 3 seconds. See the wording there, average velocity. So that just means we're finding the slope of our secant line, which we did last class and which I did for the homework check. And so when you're finding the average velocity between from t equals 1 to t equals 3, again, I'm just going to find the slope of the secant line, which is going to be s of 3 minus s of 1. That's our y2 minus y1, if you will. And then we have our x2 minus x1, 3 minus 1. All right, now, find the slope of that secant. We got in the denominator a 2, but now I got to find s of 3 and s of 1. All right, so now if I find s of 3, Again, I always like to do it over on the side. S of 3, I'm going to substitute in here. So we got 80 minus 5, 3 squared. All right, so I take 3 squared is 9 times 5 is 45. I'm going to get a 35 there. All right, I also can find S of 1. Same idea, plugging in 1 for t. All right, so let's see here. 80 minus 5 times 1 squared. 1 squared is 1, times 5 is 5, so this is going to be a 75. All right, now I'm going to substitute that in, so I got a 35 minus 75. And let's see here. I'm going to have a minus sign, that's for sure. Minus 40, I believe. Yep, minus 40. Divided by 2, I get a minus 20. And again, I believe time, which is our kind of our x value, is in seconds, and our y value is in meters. So this is minus 20 meters per second. All right, which means the pebble is moving down, the average velocity at that point. All right, now, here's where things get crazy, where we start to do something new. We get to B, and B is saying calculate the velocity of the pebble at t equals 1 second. So because we only have one value, t equals 1, that's telling us that we're finding an instantaneous rate of change, right? In the example A, or part A, we had t between t equals 1 and t equals 3. Now we have t equals 1. So now what I'm going to do is use that new formula we got, all right, where I'm going to find the limit as h approaches 0. And again, just in scientific or in function notation here, so we're going to have a s of t plus, or I'll go with t plus h minus s of t. So again, that's our y2 minus y1 all over h. But we're specifically doing this at t equals 1. That's where we want to find the instantaneous velocity. All right, so now, all I'm going to do here is I'm going to put a 1 in here for t. Nothing crazy. So as finding the limit as I push those 2 points together. All right, so I have s of 1 plus h minus t is s of 1. And again, we have h. All right. So now, let's see here. I already got s of 1. That's good. That's a 75. But now here's the tough part. Is in this function, I'm going to have to substitute a 1 plus h. I'm going to have to put a polynomial into this equation. All right. So where am I going to do that here? I want to make sure I have enough room. All right. I'm going to erase this here. I'm going to have to, fortunately. S of 1 is 75. I'm going to need that information that I found out here. Whoa. All right, so here we go. Still a little wet. All right, so again, I'm going to mark that down. S of 1 was 75, we figured it. Because again, I'm going to need that information. All right, so again, looking here. So I've got the limit as h approaches 0. Now, on the top here, again, I got to substitute a 1 plus h in for my t here. So it's going to get messy here, all right? So I've got 80. I'm going to put it in square brackets, so I separate it. Minus 5. Again, for t, I'm going to put in a 1 plus h squared. Minus s of 1, which again, we had to figure out for here to here, which was 75. All over h. Now, here's what we're trying to do in this situation. Is we're trying to substitute a 0 in for h. But the problem right now is h is in the denominator. So I can't divide by 0. All right, so I'm going to have to work through this a little bit, do some little manipulation of the formula to get rid of that h so that I can substitute an h in, because again, h is approaching 0. It's not quite 0, but it's close enough where you can say it is 0. All right, so now I have the limit as h approaches 0. All right, I got to do some calculations here. So I got that 80 there, minus 5. Now, I got to take 1 plus h squared. It's a binomial squared. And hopefully you know the shortcut to this instead of doing it the long way. But if you don't, you can always do it the long way over on the side and substitute it in. But to do a binomial squared, I take 1 and I square it. Well, 1 squared is 1. Then I go 2 times h times 1. That's a 2h. Then I take the h and I square it. So that is a quick binomial squared. So I'm just expanding what I have inside those square brackets, and I can't forget my minus 75 over there. And of course, the problem is this is all divided by h. All right, whoops. That's squared on that h, and that's in brackets. There we go. All right, now, rainbow rule. I'm going to expand that negative 5 out. So again, I have the limit as h approaches 0. Again, I'm going to keep it in square brackets, keep it separated. So I got 80 minus 5 times 1 is, or negative 5 times 1 is negative 5. Negative 5 times 2h is a minus 10h. And then I have a minus 5 times h squared, which is minus 5h squared. Minus 75. And again, the problem here is we're all over h. All right, now that I've figured out everything in the square brackets, I really don't need them. So I'm actually, instead of writing this all out, I am going to get rid of them. I'm not doing anything anymore. I'm just using them to keep it separate. There we go. Now, I can kind of not cancel some stuff out, but simplify things. I have an 80 minus 5. That's just a 75. And then I have a minus 75. So these numbers are, I guess, canceling each other out, really, because that's a positive 75 and this is a minus 75. So put those together, I got a 0. So now what I got is the limit as h approaches 0. I've got a minus 10h minus 5h squared. And of course, the problem here is I'm dividing by h. I still can't put a 0 in because I can't divide by 0. But here's a little trick here. Is the top terms. I got a minus 10h, a minus 5h squared. They have an h in common. So I'm going to factor out an h. All right. They also have a 5 in common. But the key thing is they have an h in common. All right. So now I have the limit as h approaches 0. I'm going to factor out that h that I was talking about. So I'm going to have a minus 10 here, and then a minus 5h in here, and of course divided by h. Now, the reason that I factored out that h was now I have an h in the top and h in the bottom. They divide each other out. And now all of a sudden, I don't have that h in the denominator. And so I've got here the limit as h approaches 0. Well, I got whatever's left here, minus 10 minus 5h. Now I do not have an h in the denominator. So now I can plug in that h. H is 0. Well, that just means this minus 5h here is gone, right? Because I plug in a 0 in there. And so my answer of what's the instantaneous rate of change, what's the exact speed at t equals 1 second, it's minus 10. And again, what we're talking about here was meters per second. So again, we don't want to find the average. We want to know right at t equals 1, what's that speedometer reading? Minus 10 meters per second. Any questions at all? Okay, just waiting this time. Wait. Nope. Okay. All right, we're going to try another one of those. A little bit tricky. Definitely takes some practice here. And I will tell you this, working through the calculations, You don't want to go fast. You want to make sure you do it right, because there's nothing worse than making one little small error up here and nothing will work out for you. It's a nightmare that way. All right, so I'm going to go on to example 2. Just going to do 2 examples. There you go for Erica there. Back. All right. So again, example 2. All right, says a toy rocket. A toy rocket is launched straight up in the air, such that height s in meters at t time in seconds is given by this equation right here. S of t is equal to -5 t squared plus 30t plus 2. And we're looking for what is the velocity at t equals 2 seconds. So again, we're looking for an instantaneous velocity. Again, the difference here is we're given one value. And we want to know that value, the speed at t equals 2. All right. So again, because we're using finding an instantaneous velocity, we're going to find the limit as h approaches 0. All right. Our first value, we're going to sub in. We're going to have 8 or s of t plus or 2 plus h. All right. So we've got the 2 plus a little bit more, just a little bit more, so much you can't even tell, minus our y2 value, which would just be s of 2, all over h. All right, now s of 2, again, that's something I like to go figure out over on the side. That way it's a little bit neater, which just means I'm going to plug a 2 into this equation. All right, so let's see here. S of 2 is equal to, let's see, I got -5, 2 squared, plus 30 times 2, plus 2. All right. Let's see what I'm getting here. That's 2 squared is 4 times -5 is a -20. Plus 60 plus 2. All right, well, -20 plus 60 is 40. Add 2 is 42. All right, so I got my S of 2. Now, the reason I'm doing that is because I'm going to have to plug 2 plus h into this formula to find S of 2 plus h. So here we go. Again, I'm going to find the limit as h approaches 0. I'm going to have to sub, and I'm just to keep it neat and separate, again, I'm going to go with my square brackets. All right. And so I'm going to plug in here. So I got a -5. Now where there's a t squared, I'm going to put a 2 plus h squared plus 30 times my 2 plus h plus 2. I don't have to do anything there. And then that's going to be subtract S of 2, which is 42. And of course, the problem here again is it's all over h. All right, so if you weren't good at polynomials after today, hopefully you gotten a lot better. So here we go. Equals the limit as h approaches 0. All right, so again, I've got to do a binomial squared. I do it the quick way. So just a little recap. I take the first term and I square it. So 2 squared is 4. The next term, I go 2 times the second variable, I guess, and times the first part. So 2 times h is 2h, times 2 is 4h. And then I square the last term, which is h. So I'm going to have an h squared. Whoops. H squared. There we go. So that's in brackets. That's just that part. Then I got this part. 30 times 2 is 60. 30 times h is 30h. And then I got this plus 2. And again, I can't forget about my minus 42. And the problem we have here again is we got to divide by h. All right, which is 0 right now, and it's close enough to 0 to call it 0. All right, whew, still getting her together here. So now I'm going to do the rainbow rule here with this minus 5. So I've got the limit as h approaches 0, key part here. All right, I'm not going to use the square brackets anymore. I'm not going to need them, but minus 5 times 4 is minus 20. Minus 5 times 4h is minus 20h. Minus 5 times h squared is minus 5h squared. All right, so that's just expanding through the brackets. You know what? I got this 60 and this 2. I'll put them together for 62. Plus 30h. Minus 42. And again, all over h. All right, now here's a big key where you can figure out whether you're kind of doing these things or not. A bit of a checkpoint. I've got a minus 20 and a minus 42. Put them together, I get a minus 62. I get a plus 62 here. So essentially all the numbers are canceling each other out. There we go. So that can simplify things quite a bit. So now I'm going to continue on here. Equals the limit. Now I can also put my h terms together. I have a minus 20h and a positive 30h. Well, that's put them together for a positive 10h. And then I have this minus 5h squared. All over h. Things just got a whole lot simpler very quickly, which is great. Now, again, the whole problem here is that I want to substitute 0 in for h, but I can't do that because it's in the denominator. But just like we had last time, on the numerator, they have a common factor of h, so I'm going to factor out that h. And so this time I get, factor out the h. I got a 10 there, and then a minus 5h. Again, all over h. And again, the reason that I factored out that h is so that I can divide these two out. And now I've got the limit. As h approaches 0, I've got 10 minus 5h. Because I no longer have that h as my denominator, I can plug that 0 in. And now my answer is 10. Because that 5h becomes 0. And again, we were talking about our velocity, which the y's were in meters. The x values, the time was in seconds. All right, so that is, again, finding well, in this case, we found the speed both times of the instantaneous velocity. And again, the way to tell the difference between a question with average velocity and instantaneous velocity is average, you're going to get 2 points, two x values or t values. With instantaneous, you only get 1. All right, so I only did not only, but I did the first 2 examples. Feel free to try out the 3rd example on the lesson. But again, this is something I would definitely suggest making sure that you have some practice at for your homework, because it's very, very easily to get lost in the algebra. There's no doubt about that.